All right, let's talk about the invisible engine that powers pretty much every piece of technology you touch every day: data structures. We're going to dive into what they are and why they are the absolute foundation of any efficient, professional-grade software.
I mean, have you ever really stopped to wonder about that? Why is it you can scroll through thousands of photos on your phone in a flash, but sometimes your social media feed just stutters? Well, the answer, more often than not, comes down to how that app's data is organized. So let's get into it.
Here's how we'll break it down. First, we'll cover the big why this stuff matters at all. Then, we'll look at the two main ways to organize data. After that, we're going to do a deep dive into two of the most fundamental types out there: the array and the linked list. And finally, we'll bring it all home to see how the pros make the right call for the job.
Okay, so first things first, why should we even care about how data is stored? Well, to put it simply, it's the hidden foundation that literally determines how well any piece of software is going to perform. You see, picking the right data structure is so critical because you're basically solving four huge problems at once. First, you're optimizing for performance, and that can be the difference between something taking a nanosecond or a full minute. Second, you're handling memory management, which keeps your apps from getting bloated. Third, you're ensuring clean data organization, which is absolutely key for keeping the software maintainable in the long run. And finally, it's the bedrock for powerful algorithms. You just can't have a fast search or sort without the right structure underneath it. So, at a really high level, you can split all data structures into two main camps. This is kind of the first big fork in the road when you're thinking about organizing information. Are we going to lay things out in a nice, neat line, or are we going to build something more like a web? On one side, you've got linear structures. The easiest way to picture this is a simple to-do list, right? Items just follow one after the other in a sequence. Then, on the other side, you have nonlinear structures. This is more like a family tree, or maybe a map of a subway system, where all the pieces are connected in a much more complex, hierarchical, or networked fashion.
An array is probably the most classic example of a linear structure. Just look at these student grades. Every element has a clear before and after. It's just a simple, orderly line of data.
And for a non-linear example, just think of a tree structure, your computer's file system, with folders inside of other folders. That's a perfect real-world tree. For today, though, we're going to stick with the linear types because they do an amazing job of showing us the critical trade-offs involved.
So let's kick things off with the most common data structure you are ever going to see: the array. If you need to remember two things about it, remember this: order, and more importantly, speed.
Now, the official definition is that an array stores elements right next to each other in one continuous block of your computer's memory. And honestly, that one little detail is the source of all its power. Because everything is in a neat row, each spot gets a number, we call it an index, and that index works just like a super precise street address.
So, an array's superpower is its insane access speed. In tech speak, we call this constant time, or O1. All that really means is it takes the exact same amount of time to get the very first item as it does to get the millionth. The analogy of a numbered parking garage is perfect. If you know you're parked in spot number 78, you just drive straight there. But, and this is a big but, here's the trade-off. Arrays can be really inflexible. They have a fixed size, so if the garage is full and a new car shows up, well, you've got a major problem.
So what do you do when you need that flexibility? What if you have no idea how many cars you're going to have ahead of time? That's when we need a totally different strategy. And that brings us to the solution: the linked list.
A linked list also stores data in a sequence, but it completely throws out that one big block of memory rule. Instead, each piece of data, which we call a node, also holds a pointer. And that pointer is basically just the address of the next node in the chain.
So its greatest strength is its dynamic size. You can add or remove nodes super easily. It's kind of like a scavenger hunt. Each clue you find tells you exactly where to go to find the next one. This makes it incredibly flexible. But what's the downside? Access is slow. To find the 100th clue, you have no choice but to follow the first 99 clues in order. There's just no way to skip ahead. We call this O of n, or linear time, because the time it takes to find something grows in a straight line with the size of the list.
This slide is a fantastic way to see the real power of a linked list. To reverse the whole thing, you don't actually move any data around. Nope. You just change where the pointers are pointing. Let's walk through it. See how node 1 starts by pointing to 2? In the first step, we just take that pointer and aim it backwards, to nothing or null.
Then we hop over to node 2. Instead of it pointing to 3, we make it point back to 1. You just repeat this all the way down the chain, and voila, the list is completely reversed. And we barely had to lift a finger. It's all about redirecting the flow.
And this brings us right to the heart of what software engineering is all about. It's not about memorizing a bunch of definitions. It's about deeply understanding the trade-offs so you can make an informed professional choice.
This table just lays it all out, crystal clear. If your number one priority is grabbing elements by their position instantly, then it's a no-brainer. The array, with its O1 speed, is your champion. But what if your main job is completely different? What if you're constantly adding and removing things from the front of the list, say managing tasks in a real-time queue? For that, the linked list is just miles better. It's O1 for that specific task, while an array would be painfully slow. So really, the key takeaway is this: there is no single best data structure, period. A professional's job is to analyze the problem. What are we going to be doing most often? What are our limits on speed and memory? The answers to those questions are what tell you which tool is the right one for the job.
Now, there's a common misconception you'll hear, especially from people who are just getting started. They'll say something like, oh, this level of detail is only for, coding competitions or those high-pressure interviews.
But the reality couldn't be more different. These principles are woven into the fabric of all software development. The snappy performance of your favorite web app, the speed of a database query, the efficiency of a complex machine learning model, it all comes down to engineers making these exact trade-off decisions every single day.
Look, getting these fundamentals down is more important now than it has ever been. And it leaves us with a really fascinating question to think about. As the amount of data in the world just continues to explode, how are these core building blocks going to evolve? What kind of new structures are we going to invent to help us make sense of it all? Thanks for joining me for this explainer.